last time. We finished Euclid's Elements. We finished Euclid's Elements. And we talked about two interesting things. We talked about, what was it? 12.2. So 12.2 is that the area of a circle, we would in mathematicians say disk. A circle is like the crust of a pizza, whereas the disk is the pizza itself. So the area of a disk, Euclid knows, is some constant times r squared, right? This would be the modern way of saying this. The way that he would say it is a circle is to a square on its diameter as another circle is to, circles are two squares on their diameter. Does that make sense? What that means is that there's a relationship there's a quadratic relationship between the area of what we would call a disk and the square on the radius or diameter, same thing, since radius and diameter are off by a factor of 2 themselves. And then the big boss in that book, I think it was number 18, is that the same thing holds for spheres. So the volume of a sphere, which technically, again, mathematicians would call a ball, is the interior of a sphere, and the sphere is just the boundary. So the volume of a ball is some other constant, I'll just call it C prime, times the radius cubed. But he does not say anything, and I'm sure if he knew what those constants were, he would say what they are, but Euclid does not know these constants. Euclid does not know these constants. If he did, he would surely tell us what they are because of what they are. And this is where Archimedes comes in. Okay, so let's talk about pi just a little bit. So people have known about pi forever, right? What's pi? 3.14, yeah, it's 3.14, yada yada. What is the definition of pi? The ratio of, it's a ratio, it's a number. You can measure it on any, Allison, can I borrow this for a second? No, yes. In fact, all I want, if you can have it copy that, it's not too hot.
No.
So pretend this is a circle. So we can measure pi on any circle by computing the circumference relative to the diameter. Okay, so this is circumference divided by diameter. Now here's a question. What is taller? What's larger, the height of this thing or its circumference? The circumference, right? I mean, even the diameter is longer, and the diameter is obviously a lower bound for the circumference. It's not very tall. How about, I'm going to steal everybody's stuff. I borrow your how about this? This is much, much taller. So is it taller than the circumference or not? You think yes. Let's find out. Let's find out. Rip off a little piece of paper that can help us measure. Okay, here's our little ruler. So where are we on the height? On the height, we're right about there. Everybody see that? You agree with that? That's the height. Now I'm going to wrap it around. Nowhere near.
That shape is the shape's more like a cone.
It's a little bit of a cone. That's true. It tapers in. Okay, let's check the bottom. Still doesn't make it. Even
that's more referring to like a perfect tube.
That's right. That's right. So perfect tube. So it looks like this should have much more height than circumference, but pi is huge. You don't appreciate how big pi is. It's really, really long to go all the way around. It's much shorter to go this way than to go around. If you were to cut this, so I'll just make a little cylinder. Pretend this is Amelia's Starbucks is a cylinder. If I were to cut it down the middle and just unwrap it and unwrap it. Okay, so this is its height. and then the circumference is this distance, which has been unwrapped to that distance, circumference. The circumference is still, even for this mug, the circumference is greater than the height. Okay, this is something that's really, we don't recognize it because we don't see the circumference unwrapped all the time. But actually, there's one very natural object where the circumference and the height are nearly the same. Can anyone think of one? Does anyone play tennis? No, nobody plays tennis anymore. Pickleball? What do you play? Okay, but you've seen tennis balls, and how do tennis balls come? In cans of 3. So if you take a can of tennis balls, here's one tennis ball, a second tennis ball, a third tennis ball, and a little bit of room on top, and that's a tennis ball can. If you unwrap that, it's about a square. That is nearly a perfect square because it's 3 diameters and a little bit more if you were to unwrap that. Okay, so the tennis ball can is nearly made out of a perfect square. So pi is big. That's the point of this. Pi is big. This 3.14. Okay. Now lots of people have thought about pi. There's very easy to show. Let's prove a couple of elementary theorems. So here's a theorem. Pi is at least 3. Why is pi at least 3? Well, if I inscribe a hexagon, okay, and let's say that this radius is 1. So what's the diameter of the circle? It's the same as the diameter of the hexagon. Josie? The diameter is 2. Yep. And what's the circumference? Well, to go around the circle is longer than to skip across the circle and go just along the, so the circumference is has a lower bound. You decrease how far you have to walk. If you want to walk all the way around, you'll walk less if you just walk around the hexagon. And how far do you walk when you walk around the hexagon? If this length is 1, these are all equilateral triangles, so this length is also 1. And so you take 1, 2, 6, it's a hexagon. So the circumference of the true circle is at least the circumference of the hexagon. The circumference of the hexagon is 6. And so the ratio of circumference to diameter, if the diameter is 2, is larger than 3. How about another easy theorem? Let's prove that pi is at most 4. Okay, this time what we'll do is we'll inscribe a circle inside of a square. Never mind that, well, no, this has nothing to do with straightedge and compass. We're not trying to match the area inside. So again, let's make this length 1. The radius is 1. So the diameter of both the circle and the square is, the radius is 1, so the diameter is 2. Yep. And what do you think is shorter, cutting this corner or going all the way to the edge of the block? I'm thinking this is a New York City block and there's a little park and you can cut the corner. Cutting the corner is shorter. So we make the circumference larger by forcing ourselves to move along the city blocks. So the circumference is less. If we were to walk along the circle, that's less than walking to the corner. And walking to the corner is how far do you walk? What's this distance? 1, right? It's the same as the radius. And so then we have 1, 2, 3, 4, 5, 6, 7, 8, all the way around. So the circumference is at most 8, right? It's two radii units long as one city block. Pretend there's not avenues that are really 3 times as big as the city blocks. Okay, does that make sense? So the circumference, so pi is at most 4. These are things that you can prove rigorously without doing anything. Lots and lots of people did this. The Indians, the Chinese, the Persians, basically the Mayans, any civilization that wanted for some reason to measure and make something round, they did it with, they knew that pi was big, more than 3, less than 4, and they had all kinds of other estimates. In particular, one of my favorites is in the Old Testament, the Hebrew Bible. If you go to, I pulled it up here. If you go to Kings chapter, yeah, right there it is. Chapter 7. So this is Kings in the Bible. the Old Testament, the Hebrew Bible, Kings, chapter 7, verse 23. This is describing this is about the kings are like King David, King Solomon, all these old stories. And King Solomon is building what is called a molten sea. We don't know what a molten sea is. It's some kind of ritual bath, like what's called a mikvah or something. So the molten sea, he describes a molten sea in King Solomon's temple. Solomon's temple. And the molten sea, let's see, let's make this readable. Where am I? Chapter 7. Here we are. It is 10 cubits from one brim to another. He's literally making this. Okay. Allison, this came really in handy. Thanks for getting a coffee this morning. A molten sea that is 10 cubits from brim to brim. So 10 cubits. So the diameter is 10 cubits. 10 cubits. It was round all about, perfectly circular. Okay, perfectly circular molten sea. Its height was 5 cubits. Okay, we're being told the height, 5 cubits in height. And a line of 30 cubits did compass it around about. What is that saying? What's the circumference? 30. Exactly 30. The circumference is exactly 30 cubits all the way around. Now, that's a slight problem, especially for the Jews for whom this is the word of God. Because we know that pi is not 3. So what do? Well, it turns out that in the 2nd century, maybe I'll link to this. There's a 2nd century midrash, a commentary that says, if you actually want to build this thing, it looks like God's wrong, right? God made a mistake. That's a problem. That you're saying it's 30 cubits around, 10 cubits in diameter, but it actually holds a secret. The commentary says this line holds a secret. There's nothing wrong. What's the secret? You've been given the height of the ritual bath. You've been given the diameter. Why would you also give the circumference? You don't, that's extraneous information. There's one thing you haven't been given. Well, yeah, so they're struggling with pi. But if you actually want to build this thing, there's one more piece of information you need in order to build this ritual bath. How thick you make the walls. So if you measure, so the secret is thickness of the walls. I mean, look, who the hell knows, right? Obviously. But I like this commentary because it's a way to get yourself out of this big problem if you think the Bible is the word of God and God can't contradict mathematics that we know and can prove, right? So the thickness of the walls is what's secretly being told in code by God to the people building this, because if you're going to measure the diameter, you'll walk from the inside. And if you're going to measure the circumference, you'll walk around the outside. Or maybe I have it backwards. Either way, what that will tell you is the thickness of the walls of how you should make this ritual bath. And then that's okay. That's this rabbi's way of weaseling out of the fact that there's a mistake in the Bible, if you want to interpret it that way. All right. So the point is, this is something that's been around. And the fact that this is in the Bible, it's not something that's new. This is not new information being discovered. Okay, this is something that's been understood by, again, many cultures and civilizations. This is just a particularly glaring example of it appearing in a book, well, like Euclid's Elements, that's published more than Euclid's Elements, and there it is sitting right there. So people argue like this for a long time, and they have all kinds of heuristic estimates for pi. But it's not until Archimedes reinterprets everything, Archimedes changes the game. Archimedes changes the game, giving, for the first time, rigorous estimates for pi by, here's the key idea. People are trying to approximate pi. Pi is about a length, right? Pi is about circumference to diameter. You're measuring one-dimensional objects. And he changes its meaning from 1D objects to 2D. So I have to explain what I mean by that. Here's the theorem of Archimedes. This theorem will be obvious to you because you've known it your whole lives. You've heard it so much in school, but Archimedes is the reason you know this fact. So here's the theorem. The area of a disk of radius r is pi r squared. This pi r squared that you all know, love, hate, I don't know what your relationship is to pi r squared. The fact that everyone knows this formula, it came from Archimedes. He's the one that discovered this for the first time. Okay. And in fact, this is kind of the wrong, I don't like pi r squared. I like 1/2 circumference times radius. Of course, what is the circumference? 2 pi r, so half of the circumference is, if the circumference is 2 pi r, then half of that is pi r. So there's your pi r and the radius is r. Okay. So I don't like pi r squared. I like half circumference times radius. Let me explain to you why. So I'll give you two proofs. Let me give you a warm-up theorem. So the proof, and this is, the way that Archimedes was really thinking about this. He also gave several different proofs. Let's just look at an n-gon. The way Archimedes is thinking about this is you can inscribe n-gons, and you can circumscribe n-gons. And you can, this is a way of exhausting from above and from below. This is like a, I don't know, rear naked choke or something. This is like this is using the method of eudoxis to zoom in on something. It's baby calculus. It's like precursors to calculus. But let's compare circle to inscribed and circumscribed n-gon. Okay, so we have to work out what the area of an n-gon is. So here's an n-gon. It has some. Let me draw it slightly bigger. So here's an n-gon. I don't know how many sides it has. It has 1,000,000 sides over here. Whatever. It's supposed to be regular. These are all the same. I'm just going to blow this up a little bit. Okay, it has some base. The n-gon we're going to chop into n triangles. So n-gon, area of n-gon is equal to n times the area of each of these triangles. Let's say that the base is b, and the height is the in radius. So this is the height. There's a word for this, the apothem. Again, I'm not quizzing you on vocabulary. This is really the in radius, the radius of the inscribed circle. Okay, and what is that? So I have n times the area of a triangle with base b and height. Let's call this h. Is all together now. Base b, height h, area of a triangle. 1/2 base times height. 1/2 base times height. And now we're done because we have this 1/2. We have n times b. What is n times b? Circumference. If you want to walk all the way around, you walk b and you do it n times. That's the circumference. That's the circumference of your n-gon. And then the height is the in radius. And now you send n to infinity. This is, again, not how he would say it. And you have to be much more careful than what I'm saying here in the interest of, we don't need to get into the specifics of how this method of eudoxis works here. But you see that in the limit, this is 1/2 circumference times the in radius becomes the radius. And you approximate the circle from above and from below, and you recover this 1/2 circumference times radius, also known as pi r squared. Does that make sense? Had Euclid known this, he would have been very, very excited, and we would have been very happy to include it right here. He proves this fact. He knows that it's some constant. He has no idea that that constant has anything. That's a constant about area, not about length. What does that constant have to do with the ratio of circumference to diameter? So it's because Archimedes turns, this is what I'm saying here, that Archimedes turns pi from something about one dimension to something about two dimensions. Now, if you want to look at the ratio of circumference to area, area of the circle or the disk to the area of the square in which it's embedded or that's contained inside of it, you can do that. And so because of that, so then Archimedes was able to give rigorous because now you don't have to do anything. You inscribe a hexagon, you circumscribe a hexagon. Obviously, the inner part is less, and the circumscribed hexagon is more than the area of what's inside. There's even a moment here where you all agreed with me. So I think it's clear that this straight line is shorter than going around. Here, that you would cut the corner, this is a little subtle. You agreed with me. You said, yes, of course, going to the edge of the block and around is longer than going along this curve. That's something we really should have proved. There are all kinds of things like this that seem natural and are wrong. Let me give you one example. Hopefully this won't take us too, I really shouldn't. Let me give you an example of things going wrong. Here's a theorem. The theorem is that pi is 4. Okay, how do you prove it? Well, you take the square outside, and we know that that's not really the circumference, right? We saw that the circumference of the square is 8 and the diameter is 2. The handwriting is really, this is what happens when I'm trying to move ahead. Hopefully you guys still, you've known me long enough now, you can read the chicken. You've learned chicken, right? You can read this chicken. So if this length is 1, the diameter is 2, the circumference is 8, we figured all that out. Let's cut down how much we waste by going halfway, cutting into the circle and going back up. Isn't that better than going all the way around? And we'll do the same thing here and here and here. So this is our new path. What is the total length of that path? What is it? It's exactly the same as the square. There's no difference between going in and over versus going up and around. We haven't changed the length at all. The circumference is still 8, and the diameter hasn't changed. Anyway. That's true. Diagonally would change things. Diagonally would change things. I'm doing something else to make a point. Okay, just to make the point that what we've done is not actually rigorous, and what Archimedes does is rigorous, and I'm just, in the interest of time, skipping what he really does. I just want to give you the flavor of what he does. Okay, but the caveat is you can't do things by flavor in math. You can get false statements. Okay, so what am I going to do next? Well, I can do better than this. I'll cut this area, and instead of going up to that corner, I'll come down. Right? That'll be an even closer approximation to the circle. And again, and this one I'll cut also and get even closer. And so you keep doing this, getting closer and closer all the way around. The circumference is always 8. So where does this argument break down, right? We have to be very, very careful about the fact that the length of this while the limiting figure will indeed be the circle, its length is not at any point approximating the true length of the circle, because you're never going on diagonals, because you're always doing this extra thing. Okay, so you have to be very careful when you draw pictures and start arguing with pictures. All right, so because Archimedes didn't have to argue with pictures, he had an inscribed hexagon, which he bisected to an inscribed 12gon, which he bisected to make an inscribed 48gon, and an inscribed whatever 48 times 2 to the 10 is. Right? He could go as much as he wanted, and he was always inside the area. He never had to argue with length. He never had to worry about whether the lengths that he was drawing were or weren't larger or smaller than that of the circle. So he was able to give rigorous estimates for pi by replacing, this is what I said above, by replacing arguments involving curves and lengths of curves, involving lengths of curves, which is very subtle, with ones involving areas, and areas of objects. One object sits inside the other. There's nothing to argue about, right? You have an inscribed polygon, you have a circumscribed polygon, x-scribed polygon, involving areas where there is nothing subtle. Okay, does that make sense? He did not stop there. He worked on so all kinds of other theorems that you know. So using this method of by combining this method of exhaustion, which really, you know, we should give credit to Eudoxus for initiating it, but in the hands of Archimedes, it became this magical thing. And his ideas of leverage. Remember, we talked last time about how an object 10 times away from the fulcrum pushes 10 times as hard as an object that's only one distance away from the fulcrum. So he's using method of exhaustion with the lever. He is, by combining this method of exhaustion and leverage, we can say, Archimedes is able to explode our understanding of not rectilinear shapes, which Euclid already had a pretty good control over, but curvilinear shapes, And all the theorems that you know today, you know, and I hope love, like the surface area of a sphere. Anybody remember what the surface area of a sphere of radius r is? It's 4 pi r squared. So if you look at a sphere and I don't know, you have like a round ball and you have to cover it with chocolate. And the question is, how much chocolate do you need? You need 4 pi times the radius squared of chocolate to fill it perfectly, right? If you have a tub, if this radius is r and you have an r by r tub of chocolate, how many of those do you need? You need about 12 tubs, a little more than 12 tubs, because pi is about 3 times 4 is 12. You need 12 of these tubs if you want to perfectly cover the sphere in chocolate. Is this a bad analogy? I'm getting blank stares. You've had to put, okay, let's move on. You understand what why is it, why is this? Notice that this is 4 times, if I just took the disk, the inside disk in here, that has area pi r squared. And the question is, how come it's exactly 4? I'm linking you guys to a video that I encourage you to watch that explains exactly why it's 4. 4 times the area of this great disk. Okay, does that make sense? Then he proves, so this is another theorem of Archimedes. Here's another theorem of Archimedes. Remember the big boss? The big boss at the end of book 12 is that the volume of a ball is some constant times r cubed. Euclid doesn't know what that constant is. He would have loved to know what that constant is. What's the volume of a sphere? 4/3 pi r cubed. Where are we? Yeah, the volume of, again, I'll say ball. Normal people would say sphere here. Mathematicians insist on calling the surface of the sphere and the interior of the ball. 4/3 pi r cubed. Those of you that know calculus will see that the derivative of the volume of the ball, you bring the 3 down and make the 3 into a 2. If you're differentiating a polynomial, if you're trying to compute a ball, then the boundary of that ball is the sphere. The boundary is like the derivative. Like a little slice of the ball is the sphere, and these areas are getting added up to make this volume. So hopefully you've seen that before. Right, so all of these constants, there's not this slew of different constants, one in every dimension, one for every calculation. There's only one constant. If you know pi, you know everything else. Everything else is like 4/3 times pi or 4 times pi. Okay, pi is the one constant. He made pi a thing. You can define a constant for the ratio of the surface area of a sphere to the disk or the square on its diameter, right? That's going to be some other constant. Or the ratio of the volume of a ball to a cube on the day. That's going to be some other constant. You don't need any other constant. That's what Archimedes discovers. Once you have one constant, you have everything. Archimedes also discovers, so not only does he work on these kinds of circular objects, he also proves, so here's another theorem of Archimedes, the quadrature of the parabola. So, or parabolic sector, I should really say. So what does that mean? If I have a parabola, now what does parabola mean to them? Okay, we have to talk a little bit about what a parabola actually is. What's a circle? Let's come back to this in a second. What's a circle? You have a compass, yeah. If we go all the way back to like surveying, you put a stake in the ground that you have a center, right? It has a center, which is a stake in the ground. And then you have a radius, which is some rope. Radius is rope tied to the center and kept taut. And then you walk around, and that's what makes a circle. Okay, so here's my stake in the ground, and here's a rope, and as I walk around, this sweeps out a circle. Like the Egyptians, like the Persians, like the Indians, like the Mayans. I think this is something that anybody, you give a child a stick and a rope, they'll put it in the ground and walk around and make a circle, right? It's like the most obvious thing that you would think of. How about what's an ellipse? What's an equation for a circle? Perfect. Of course, the understanding that algebraic equations correspond to geometric objects, we do not get until Descartes. The Cartesian plane is, so this is anachronistic to talk about, but we modern people can understand these things. They did not understand these things. What's the typical equation of an ellipse? Yeah, it could be r squared, but then you can divide the r squared into, you can change the a and the b so that it's just one. Okay, so an ellipse, what is an ellipse? An ellipse is an object like this. So this is something that has major axis A and minor axis B. It's a shape like that, but what is it geometrically? Do you know, Amelia? Does anyone know? Geometrically, it's two, not just one center, but two centers. The two centers are called foci. So these are focuses. Each of these is a focus, and the foci is the two of them. So you put two stakes in the ground, and then you tie a rope between the two, but that rope is, if the rope is taut between the two, there's nothing to do. But if the rope has any slack in it whatsoever, you can pull that rope taut. In other words, if this distance is u and this distance is v, so u is the distance from the end from where you're standing to one of the stakes in the ground, and v is the distance to the other stake in the ground. As you walk around, so if u plus v is the length of the rope, which is fixed, so you keep that length fixed, as you walk around, you will trace an ellipse. Okay, does that make sense? So just imagine, I'll try to draw a 3D picture. So imagine you have one stake in the ground over here. What happened? One stake in the ground over here. You have another stake in the ground over here. You have some rope that's tied to both of them. You pull that rope taut. You walk and pull that rope taut. And then you just walk around. And as you walk around, the shape that you will form is an ellipse. Okay, and if you think of those two foci coming together to a point, if you keep changing the stake so that there's a single point in the middle, so that the two foci come together to one, what will you get? I heard somebody say, yes, a circle, right? It's hopefully it's clear that if the two sums are actually going to the same point, then that's the same thing as a circle. So as foci come together to one center, the ellipse turns into a circle. Okay, does that make sense? And so then the question is, what is a parabola? So a parabola is a generalization of an ellipse. In fact, eventually through work of a guy named Apollonius, they understood all of these things as conic sections. You know what a conic section is? Exactly. You take a cone and you slice it. You slice a cone along some plane. And what is the intersection? This is the conic section. What is this intersection of a cone with a plane? It turns out this oval shape is an ellipse. It turns out that this oval shape is an ellipse. Unless the plane by which you cut is actually parallel to the slope of the cone itself, if you cut by a parallel plane, if this plane is parallel to the slope of the cone, then what will the intersection be? Parallel planes give parabolic intersections. That's what the para is. And what if you cut at an even steeper incline? If it's more than that incline, it's hyper the parabolic one, you get a hyperbola. That hyperbola, now a hyperbola, maybe you guys know about hyperbolas. This is like a total crash course in the kinds of, what is a hyperbola? What's a typical hyperbola? Yes, it's like, what's the typical equation of a hyperbola? Like y equals 1 over x. Okay, so y equals 1 over x looks like that, and it looks like that. So it has two parts. Where's the other part of this? The cone is actually a pair of cones that continues. And if you cut at a plane that's parallel, then that plane never hits the cone again, bless you. But if you cut it more than that, if you go farther, hyper, the parabolic slope, then it will again catch up to this over here somewhere and have another intersection. Okay, so that's the two little sectors of the two segments of the two distinct components of the hyperbola. Okay, does that make? I'm not proving anything. I'm just telling you some funny facts. And so this is why the word parabola and hyperbola were invented. They were coined by a guy named Apollonius. Around the same time, this is also like 250, 200 BC, 200-ish BC, just FYI. And so this intersection is called a hyperbola. Okay, that comes all the way back to what was a parabola. Just after Archimedes, people could understand it in terms of conic sections. So this is a conic section. You take a cone and you slice it by a plane, and what do you get at the intersection? What is a parabola to Archimedes? Parabolas have two things. Instead of two foci, it has a focus. It has one focus, and it has a directrix, a line called a directrix. Okay, let me go somewhere where I have some more room. Okay, this is, I want you to know a little bit about how they thought about these objects, because they didn't have algebra. They couldn't say a parabola is y equals x squared, right? But I guess I should have. Can someone tell me a typical equation for a parabola? Y equals x squared. Okay, I should have asked first. Yeah, y equals x squared is a typical parabola. That is not how they could possibly have thought about it until Descartes. So how did they think about it? They thought about it as a focus and a directrix, which, by the way, you can also think about both ellipses and hyperbolas in that sense. So what is a hyperbola? What is a parabola? What is a parabola? It is the locus, in other words, the set of all points, the locus of all points, bless you, equidistant to the focus and directrix. Okay, so let's do an example. Yeah, let's do an example before we try to understand it in general. So here's an example. Here's a point. I'll call it P. Maybe I should call it F for focus. F. F is the point 0, a quarter. And L is the line y equals negative a quarter. Nargis, I lost you. I'm going fast. I'm trying to cover some of what I hope to cover this semester, and I'm stepping on the gas. Just L for a line. Yeah, we could do D. This is the directrix is a line. Yeah, we could use D. The focus is a point, the directrix is a line. So, I haven't explained it to you yet. I'm trying to get to the explanation of what a directrix is. So I want to understand. So where is this point? 0, a quarter. If this is 1, this is a half, this is a quarter. So here's the point F. And similarly, this is -1, -1/2. Here's -a quarter. And L is this line over here. That's L. Maybe I should have called it D. This is the directrix. Directrix. Okay, I want to find the set of all possible points. So let's call this like x, y. So that the distance to the focus is equal to, they're equidistant between the focus and the line. Now, what's the distance to a line? What's the difference from a point to a line? What do you think? Yeah, you just go as close to the line as you possibly can, right? You drop the perpendicular to the line, and that's the distance. So you're about to tell me what the distance is? Y and a quarter. Y is this distance is y. You need to add another quarter to get to the line. Okay, so perfect. So distance to the directrix is equal to y plus a quarter. That was easy. What's the distance to the focus? Distance to the focus. If I'm at x, y versus 0, a quarter, how do I figure out this distance? Anybody remember? Something called the Pythagorean theorem. What's the x part? X minus 0. So this is x minus 0 squared. And how much are we getting in the y part? The whole height is from the x-axis. The height from the x-axis is y, but I'm not going that far. I'm going y minus a quarter, y minus a quarter. And the sum of the squares of this part and that part will be this length squared. So let's say distance squared to f, because I don't want to take square roots. Square roots are annoying. In fact, let's square the distance to L also. Okay? Everybody with me so far? And the point of being on a parabola is that you're equidistant to the focus and to the directrix. So the distance to the focus and the distance to the directrix, or their squares, have to be the same. Okay, so we're going to set these two things equal to each other. And let's see what equation we get. You want to take a minute and work on it? Take a minute and unpack all of this algebra and work out the equation. Talk to your friend. You guys are quiet. Okay, everyone's just calculating.
I'm lost.
We have set two things equal to each other. Are you lost in how to do it or how we got here? Both. What we said is that the definition of a parabola is it's the set of all points that where if you compute the distance to the focus or the distance to the directrix, you get the same thing. Amelia, you got it already? Okay, don't tell us yet. That's just a definition. Does the definition make sense? This length, yeah, let me draw another version of this picture so that here's a focus and here's a directrix, line L. So this point, the distance here, whatever this distance is, had better be the same as this distance. Okay, and we're trying to work out what that is in algebraic terms. In the case where the focus is at 0 1/4 and the directrix is at y equals negative 1/4. I have to do a little calculation for that to come out nice in my head. Okay, so first we have to figure out what the distance to the focus is. So for any point x comma y, we said the distance to the focus is this, or the square of the distance to the focus is this.
Because
It's x minus 0 squared plus y minus 1/4 squared. That's just the formula for the distance between 2 points. The reason that's the formula is because of the Pythagorean theorem. Base squared plus height squared is equal to hypotenuse squared. Does that make sense? And what about the distance? What about this distance? The distance to the directrix is just y plus another 1/4. Well, y is the height. We want the perpendicular distance. So this is the x direction, and this is the y direction. So y, what does x comma y mean? It means you go x units over and y units up. So if we've gone y units up, what's the distance to L? I have to go another 1/4 more to get from here down y and another 1/4 until I get to L. Does that make sense?
Yeah.
So then
because we made it to be that way.
that's the definition. The definition of the hyperbola is the set of all points x and y for which this thing and this thing are exactly equal. So now we have to figure out what does that actually amount to. Okay, so let's try to solve it. I'll put it here again. X minus 0 squared plus y minus 1/4 squared is equal to y plus 1/4 squared. Okay, let's work with this side. Y plus 1/4 squared is y squared plus 2 times y times 1/4 plus 1/4 squared. I don't even know what that is. It's 1/16, but never mind. We don't need to know what that is. So far, so good. How about on the other side? I get an x squared, x minus 0. I'm not going to do anything with the 0. And this is a y squared minus 2 times y times 1/4, and then plus 1/4 squared. There's a 1/4 on both sides. I can subtract that off. There's a y squared on both sides. I can subtract that off. Negative 2y times 1/4 is a half y. So if I add a half y, I add a half y to both sides. Then on this side, all I'm left with is x squared. Okay, so on this side, all I'm left with is x squared. On this side, what I'm left with is 2/4 y, which is a half y plus another half y, is y. Y equals, the reason y equals x squared is a parabola is because secretly what's floating around is a focus and a directrix. And the parabola y equals x squared is exactly the set of all points where the distance to the focus is the same as the distance to the directrix. Okay, does that make sense? So you see there's a very complicated object. It's a curve. It's not a radius. It's something really, really complicated to work with. And Archimedes proves, so here's the theorem of Archimedes. This is really, if the other things were precursors to calculus, this is calculus. I'm sorry. He understands calculus. He says that if you have a parabola, if this is a parabola, so secretly there's some focus and directrix, I won't even draw them, and you take a cut of that parabola by a line segment, then this is the parabolic sector. So the area of the parabolic sector, he works out what that area is. That's what I mean by the quadrature of the parabola, or quadrature of the parabolic sector. What you do is you take a line parallel to this line that's tangent to the parabola, and you draw this triangle. Let's call this triangle T. T is triangle. Triangles, we know the quadrature of a triangle. He shows that the area of the parabolic sector is exactly 4/3 times the area of the triangle. This is a crazy argument. In the interest of time, I won't even give what his argument is. But this theorem, Amelia.
Just use like a straight edge compass.
Well, No, he really uses calculus. What he observes is that, remember, we just cut this, the whole parabola is an infinite object. We cut it by a straight line, and then we form this triangle. But look at what this is. What's this area? What's this shape? It's a parabola that's been cut by a straight line. So he says, wait a second, if I take a little tangent line here, parabolic, a parallel line that's tangent here, and I make another little triangle there, maybe I can understand something about the relationship between this triangle and that triangle and that triangle and that triangle, and then I can fill up the entire area with these triangles that all have a nice relationship with one another. And it turns out that what he's adding up, yeah, this will really take us a little bit outside of what I think there's an infinite, okay. He understood something about adding infinite series in a very deep way. You guys know Zeno and Zeno's paradox? Have we talked about Zeno? Okay, let's talk about Zeno for a second. Because Zeno's also ancient Greek just before this time. Zeno's paradox. This is good. We should just know lots and lots of stuff, even if I'm not giving you the proofs of these facts. We should know about these things. So Zeno says, I can never get to the blackboard. If I want to try to get to the blackboard, I first have to get halfway towards the blackboard. We did talk about it. And in order to get, even if I manage to get halfway, I still have to go halfway towards the blackboard. And if I still have to go halfway, I'll never actually make it there. Okay, which is obviously wrong because here I am walking to the blackboard and touching. In fact, it's even worse. He says, in order to make it all the way to the blackboard, I first have to go halfway. But in order to get halfway, I first have to go a quarter of the way. And before I can go a quarter of the way, I have to go an eighth of the way and a 16th of the way. I can't actually move. Motion is impossible. Not only is it impossible to reach the blackboard, I can't leave this spot. Okay, so all of those things are complete nonsense. And the reason it's a paradox is what's wrong with his argument. And people are really struggling with this. What they were really struggling with is infinite series. So if you add 1 plus a half plus a quarter plus an eighth plus a 16th and so on, like there's a way of thinking about this. Actually, I'm being a little too mathematical by adding that initial 1 to it. Let's just think about a half plus a quarter plus an eighth plus a 16th. And yes, why? So this is part of what Archimedes had to face in this argument, because it turns out he's going to add one of these geometric series in order to work out what this area is. And the way that he thinks about it, again, I'm reinterpreting things a little bit and simplifying them, is if this is 1, then halfway is right here. So this is a half. And then what's a quarter? Well, it's half of a half. What's left over is a half. And so a quarter would be that. Everybody happy with that? And then what's left over is a quarter, and I want to add an eighth. Well, an eighth is half of a quarter. So I need to add up, that's an eighth. So this is a half, this is my quarter, this is an eighth, and I can chop over here a 16th, and I can chop over here and make 1/32, and so on. And as I keep, like every time, he's thinking about it like we're playing a game. Okay, we play a game. We cut the thing in half, I take half. You take nothing. Then we'll cut it again in half, and I'll take half, and you still take nothing. And then we'll cut that in half, and I'll take half, and you'll take nothing. And what do you get in the end? You get nothing, I get everything, right? So that's why this adds up to 1. A half plus a quarter plus an eighth plus a 16th. He's thinking of as adding to 1. What if we had something more? Let's do something a little bit more subtle. How about 2/5 plus 4 25ths plus 8 125ths plus 16 625ths? 4 of these would give us 500, so 1 more is, and so on, right? So I'm adding just multiples of, or powers of 2/5 to the end. This isn't what he did, but the way I would think about this, the way that Archimedes could have thought about this is the following. In the same way, we're going to chop this into 5 equal pieces, okay? 1, 2, 3, 4 cuts makes 5 equal pieces. And in the first stage of the game, I'm going to take 2 of them. Okay, 2 are for you. The last one we're going to argue about. We're going to chop this into 5 equal pieces. 1, 2, 3, 4 cuts, 5 equal pieces. 2 of those pieces is 2/5. Sorry, we're gonna 1 of those will be for you. 2 of them we're gonna leave alone. So 2 for me, 1 for you, and 2 are up for grabs. What's 4/25 is 2/5 of 2/5. He's really thinking about this as 2/5 times 2/5. So here are 2 of the fifths. We're going to cut those 2/5 into fifths, and we're going to take 2 of them. So here's 4/25. Does everybody see that? And the opponent gets 2 for the price of, so every time I take 2, you take 1. And then there's 2 left over that we have to argue about. And we're going to cut these into fifths. So what is 8/125 is if I cut this into fifths. This gets a little harder to see. And I'll take 8 of them. How shall I draw this? 1. What I should really do is take these 2/5 and forget that they were cut initially and just cut them like this. 1, 2, 3, 4. There we go. And I'll take 2. So that's really, because there's an extra line here and there's an extra couple of lines here. That's really 8/125. What's left over for you is 1 of these packs of 4/125. And then what's inside is up for grabs. This is a little complicated. I should have chosen an easier number than 2/5. But maybe you see what is this going to add up to? When we are done divvying up the unit area, every time I took 2, you took 1. Two-thirds. So this argument is related to the argument that Archimedes uses here to get 4/3. Let's not go into it. What I wanted to say is we do not have time. We could spend, again, an entire semester, just like we could have spent an entire semester on Euclid's Elements, going through really every last detail. We can spend an entire semester just on what Archimedes accomplished in his relatively short, by modern standards, lifetime. So he's doing all kinds of amazing things. He is, by recognizing that all of these other constants, the volume of a sphere, the surface area of a sphere, the area of a disk or a circle, can all be expressed in terms of one single constant pi. He's able to analyze pi and get a really sharp estimate for it. I want to skip ahead to talk about what happens to pi later. So I forget what chapter this is in the book, but when we get to Newton, we hear about what happens to pi in the beginning of the modern era. By Newton, we're in the modern era. So let's skip to the 1650s, or maybe 1660s by then. Let's call it mid 1600s. Let's skip to the middle of the 1650s. The mid 1600s is the 1650s. There we go. So Newton is a young kid. He's home from his studies in Cambridge. Yeah, so that means I should be able to tell what it is. It should be like 1665, I think. Something like that. The reason I have in mind that date, maybe 1663. Anybody know what's happening in Cambridge at the time? He is quarantined at home because of the plague. There's a breakout of the plague. And what do they say? Everybody in Cambridge, go home. There's not going to be any school right now. We need to stop the spread. And so he's quarantining That's not right. That's not right either. Help. Quarantines at home. There we go. And he's got a lot of time on his hands, and he sort of discovers calculus. This is even before he's discovering the full strength of calculus. He's playing with infinite series. He's playing with things like this. Discovers, let's say, infinite series, in particular, infinite polynomials. I'll try to explain what I mean by that if I have time. If not, maybe I'll send you to a YouTube video where this is explained. Infinite polynomials. And as a result, discovers a way of computing pi that's way, way, way more efficient than the way that Archimedes and people who followed Archimedes were doing it. That's infinitely more efficient. Well, infinitely is a little strong a word, but whatever. More efficient than just bisecting n-gons and computing in areas and out areas, than computing areas of inscribed and circumscribed n-gons, or huge n. So let me tell you a little bit about what that is, or should I? What's more efficient? I think I could just play you the video. Now let's just talk about it. I'll send you home to watch a video. Okay, you can watch a video at home. Let's use our time efficiently. So let me just give you a overview of what he's thinking about. He starts with the binomial theorem. Maybe you guys know the binomial theorem. Let's talk about the binomial theorem for a second. Do we know what Pascal's triangle is? Is this something that people have heard? Pascal's triangle, which, like everything else, was not originally due to Pascal. By the way, even this thing that Newton discovers, I should mention, this computation of pi, that's very efficient, was known in India 200 years before by an Indian named Madhava. Madhava in the 1400s had a very similar idea. The followers, this is an interesting philosophical discussion. Like, if a tree falls in the woods and no one hears it, does it make a sound? So Madhava is doing amazing things. He has a number of followers, but none of them really. Newton, I wouldn't say that Newton has followers. Yes, there's a British school that grows up around Newton, but Newton is afraid to talk about calculus. He doesn't have the foundational. Maybe I'll say something about this next time. I can show you if we actually look in the Principia. So he writes the Principia Mathematica. This is like where you get the laws of motion. An object stays in motion unless acted on by a force, which is like, if you think about that law, that's a crazy law. No human being has ever experienced an object continuing in straight motion without a force acting on it. We always have gravity, first of all. Okay, maybe you're thinking about a puck on an ice rink that's sliding along. Well, there's friction acting on it in a very small amount. That's what the nice thing about ice is. But Newton has these incredible laws of motion. In particular, you know the story with the apple falling on his head? What's that story about? He discovers gravity because an apple fell on his head? There's a missing component in that story, the way it's popularly told. When the apple hits his head, who knows about whether there was an actual apple or a tree or anything hitting his head, but the way I would tell this apocryphal story is that the apple hits his head and he sees the moon. He's Newton. He's another absolutely incredible person that we have to spend an entire semester dissecting his life work. And we're going to do it in 10 minutes. So the story, the way I like to tell this story is the apple hits his head. He looks up and sees the moon and thinks, what if the reason that the apple falls to my head is the same as the reason the moon stays in the sky? That doesn't make any sense. How could that be? So if you think about, so here's the Earth, and here's Newton sitting under an apple tree, and the apple falls out of the tree and hits his head. And here's the moon, very far away. I think I think we will have time to talk about the moon and what was known in the to the ancient Greeks about the moon. So here's Newton sitting here, and he's thinking the apple's falling, the Earth's gravitational pull is at what is it, 32 meters per second squared or something, falling towards Earth. And he says maybe the moon is also falling towards Earth at the same rate. The only difference is the moon is also going really fast that way. And so as the moon falls towards Earth, because of its trajectory, it actually falls this way. And now again, it's going to fall towards Earth, but because of its velocity, it's actually pointing, it's moving so fast. It's moving really, really fast this way, and it tries to fall towards Earth, but it never quite gets there. And that's why it's staying in orbit. Does that make sense? Which is actually what's going on. Okay, never mind that gravity is no longer a force. In Newton's day, it was. At least that's how he understood it, and that's a pretty good approximation to what's going on. So he's doing things that are very mathematical. He's saying, suppose that what's keeping that object in the heavens is also the thing that's bringing this that there's a universality to gravity. It acts on heavenly bodies like the moon, just like it acts on something I can pick up and bite, the apple. Okay, so this is a very deep, those are very, very deep ideas. Let's go all the way back. Before he has all of these ideas, he's playing around with infinite series. Let's talk about Pascal's triangle, which you can find in lots and lots of other cultures. There's a funny reason that it became known as Pascal's triangle. Here it is. It starts with a 1, and then it goes 1, 1. You remember that in the next line? 1, 2, 1. What comes next? Yep. Does anybody know what Amelia is doing? So there's a 1 over here. Jemima?
You add the
Correct.
other two.
Yeah, you add the 2 numbers above to get the next number. 3 plus 3, 6. 3 plus 1, 4. 1 plus nothing, 1. 1 plus nothing is 1. 1 plus 4 is 5. 6 and 4, 10, 10, 5, 1. And what's the beauty of this Pascal's triangle? It's that if you want to know what, let's say 1 plus x raised to the 5th power is. Okay, well, if you were to start multiplying all of this out, it would take a really long time. It'd be really annoying. You would get some constant. I think it's clear that the only way you get a constant is if you multiply all the 1s. Like, what is this? It's 1 plus x times 1 plus x times 1 plus x. That's 3. Here's the 4th one, and here's a 5th one. Okay, and I got to multiply all this out. And how do I get a constant term? I get a constant term by taking the 1 times the 1 times the 1 times the 1 times the 1. Okay, so that's a 1. How do I get just an x? Well, I could take the 1 and the 1 and the 1 and the 1 and the x. All right, I got to multiply, I got to massive foil this out, multiply everybody by everybody else. Or I could take an x times a 1 times a 1 times a 1 times a 1. Or I could take a 1 times a 1 times an x times a 1 times. There's all these combinations. It's really annoying to figure out what it is. But whatever it will be, there's going to be some number of x's. There's going to be some number of x squareds. There's going to be some number of x cubes. And some number of x to the 4ths. And some number, well, how could I get an x to the 5th? I got to take all of them. Yeah, I got to take the x and the x and the x and the x and the x. There's only one way to do it. So it's 1 times x to the 5th. Okay? And the answer is that there will be 5 x's and 10 x squareds and 10 x cubes and 5 x to the 4ths and 1 x to the 5th. You just read off the coefficients from Pascal's triangle. Yes, exactly. Very good. Very good. Not many people know that. 11 squared is 121. 11 cubed is 1,331. And 11 to the 4th is 14,641. Why? Because 11 is 10 plus 1. Or maybe better said, 1 plus 10. 1 plus 10. So if you stick in x equals 10 into this equation, then this is a 1, this is a 10, this is 100, This is 1,000. That's 10,000, and this is 100,000. Now, because once you get to the next coefficient, the 10 is actually too big, so you have to carry it over into the next. So it's the powers of 11 for a little while, right? 11 to the 1 is 11, and 11 to the 0 is 1. So yes, these are the powers of 11, and if you interpret them correctly, that continues forever, because 11 is 1 plus 10. So he takes this binomial theorem, and he writes it in a funny way. He says, well, how do I explain this in 4 minutes? He writes it in a funny way. Let me write it like this. If you raise it to the nth power, then here's what you do. You start with a 1, and then it's clear that this number has to be n, right? The reason it's 5 is because there's 5 different ways to choose one of the x's, and all the others are 1s. So there's going to be an n here times x. What's maybe not as clear is what happens next. What happens next is you get an n times an n minus 1 divided by 1 times 2. So it's n times n minus 1 over 2. And in the case of 5, this is a 5 times 4 divided by 2 gives you 10. The next one is going to be n times n minus 1 times n minus 2 divided by 1 times 2 times 3. This is the pattern that he observes. In this case, the pattern was known before. Let's see if we believe that. This is 5 times 4 times 3 divided by 2 divided by 3. So the 3's cancel. The 4's, 4 divided by 2 is 2. 5 times 2 is also 10. So you increment the number on the bottom, and you decrement the number on top. And he says, what if this formula actually holds in general? So this is where he breaks the binomial theorem. This is called Newton's binomial theorem. He says, what about n equals -1? Does that make any sense? Let's see. 1 plus x to the -1 is supposed to be 1 plus n. N is -1. And then I get a -1 times -2 divided by 1 times 2, x squared. Then I get a -1 times -2 times -3 divided by 1 times 2 times 3, x cubed. And then more and more terms that look like this. If we were to simplify this, so that's a 1. What is this? -x minus x. How about this? Plus x squared, right? The minus and the minus cancel, and the 1 and the 2 are the same as the 1 and 2 here. How about here? I got a 1, 2, 3, 1, 2, 3, minus, minus, minus.
Oh, no, minus.
Yeah, it switches sign again, minus x to the third, and then plus x to the fourth, and so on. So he says, what does that mean? Look at these coefficients. 1, -1, +1, -1, +1, -1. If we go back to Pascal's triangle, maybe we can think of another row here. Maybe there's a row that goes 1, -1, 1, -1, 1, -1. And what is 1 plus nothing? 1. What's 1 plus -1? Nothing. -1 plus 1? Nothing. Oh, that kind of makes sense. But, okay, that's funny in Pascal's triangle, but does this thing really make sense? Like, what is 1 plus x to the -1? It really means 1 over 1 plus x, right? And so if this is supposed to make any sense whatsoever, if I were to multiply both sides by 1 plus x, what should I get? One. I should get 1. So let's see. Does multiplying the right-hand side by 1 plus x give 1? Well, okay, let's find out. So the right-hand side is 1 minus x plus x squared minus x cubed plus x to the fourth, and so on. And I'm going to multiply it by 1 plus x. Okay, You ready? Emil, you ready? Why not? Let's do it. 1 times 1? 1. Awesome. We're off to a good start. 1 times x. Yeah, 1 times x is 1x. 1 times x is just x. Okay. And how about, how many other ways are there to get just an x term? No x squared, no x cubed. We can multiply 1 by x, or we can multiply 1 by x, which comes with a negative. So we get a negative x. How do we get an x squared? We can multiply x by x and get an x squared with a minus sign. So this is negative x squared. Is there another way to get an x squared? 1 over there times that x squared gives us a plus x squared. In fact, every time we get an x cubed over here, we'll get another one over there, just with the opposite sign. So we get minus x cubed plus x cubed, minus x to the 4th plus x to the 4th. What does that all add up to? 1. The x and the negative x cancel. The negative x squared and the positive x squared cancel. The x cubed and the negative x cubed cancel. And he's quite satisfied with this. And I will let you continue watching. I'll post the video that you can watch on your own for how Newton does the rest of this and how he turns that into a computation of pi. All right.